All right, so we want to look at some properties of matrices, and then later talk about the inverse of a matrix. So we introduced matrices as objects in and of themselves in the last set of lecture videos, and we want to sort of continue with that a little bit. I do want to look at some properties of matrix arithmetic. Kind of already hinted at the fact that the matrix multiplication as we defined it was not commutative. In other words, if I multiply two matrices and then change the order that I multiplied in, I may not get the same thing. It may not even be defined. And we'll look at that in a moment a little more in depth. But I want to talk about things that are true for matrix arithmetic, and these are a list of some of those properties. The addition of matrices is commutative. In other words, you can change the order, and that's good because real numbers behave the same way, right? So it doesn't matter the order you add matrices in. You can also regroup. This is also called the associative property, associating or regrouping. So if I have three matrices I'm adding together, I can add B and C together and then add A to it, or I can add A and B together and then add C to it. Multiplication is also associative, and we kind of talked about that. If I'm multiplying three matrices together, I can multiply the A and B together first, and then times the C, or the B and C first, and then times the A. I cannot change the order though, so there's no similar commutative property we'll see for matrix multiplication. Also, because of the fact that we don't have that, when we talk about distributing multiplication over addition, we have both a left and a right distributive law, and that's real important. So with real numbers, it doesn't really matter, right? If I have A times BC, I can write this as AB plus AC, which would be the same as BA plus CA, but that's not true with matrix multiplication. So the distributive properties we have are both a left, if I'm multiplying by A on the left, versus A on the right. And then these properties 6, 7, 8, and 9 deal with scalar multiplication. So there's a sort of a distributive property of one scalar over the sum of two matrices, the sum of two scalars as a multiple of the matrix A, and how we can distribute that. If I'm multiplying a scalar multiple of a scalar multiple, what we can do. And then if I'm multiplying a scalar basically by a product that is defined, A times B, you know, we can rewrite it this way. Basically it's saying this scalar, we can move it around anywhere we want. So unlike the matrices themselves, when we're multiplying, we can't change the order. AB is not BA, but we can move that scalar around. Okay, I'm going to actually do a proof of one of these properties. We proved a property involving the transpose, if you remember in the last set of lecture videos. I do have a homework assignment where I want you to prove a very similar property. These are not all the properties. We also have you can do A times the B minus C, for instance, and there's a left distributive law that way as well. But I'm going to look at number 5 here. I'm going to prove this right distributive law, and when you do your proof, I want you to model it exactly after this proof. So I'm going to show you how basically to do that proof. So first of all, just as a reminder from last time, matrix addition, if A and B are both the same size, then I can talk about their sum A plus B, and the ijth entry of that sum is simply the corresponding ijth entry of the matrix A. This is what that is, plus the ijth entry of B. Right, so that's easy for addition. Matrix multiplication, a little more complicated. If A is m by n and B is n by r, then I can do the product AB. Notice the inner numbers we've talked about, the number of columns in the matrix on the left matches the number of rows of the matrix on the right. And the resulting size, notice, is m by r. And the arbitrary entry in that product AB, remember, is found by taking essentially the dot product, if you will, of the ith row of A and the bth column of J. That's the ijth entry of AB, and this is what that is, right? So you take the first entry in the ith row of A times the first entry in the jth column of B, second entry in the ith row of A, second entry in the jth column of B, all the way down to the last entry in the ith row of A and the jth row of B, or column of B, right? And of course, notice there are n columns in the matrix A, and so that's where we end when we go across a row. And there's n rows in the matrix B, and so that's where we end as we go down the column. And so that is the way we define that. So how are we going to prove that? So if you remember, there's two steps to prove equality. I'm going to prove that this matrix over here on this side is equal to this one over here. And there's two steps. The first is we have to show these matrices are the same size, and then we have to show corresponding entries are equal. So I'm going to start with the first part. I'm going to let B and C be a certain size. Since I know I've got to add them together, they both have to be the same size. So I'm going to let them both be size m by n. Okay? So that's arbitrary. You don't want to make it n by n. You don't want to force them to be square. Just arbitrary. And you can use other letters other than m and n, but this is what we want to do. And then let's talk about A, the matrix A up here. Now notice I've got to do BA and CA, so that means something has to happen though, right? B and both C but have n columns, and therefore A has to have what? N rows. So that forces the number of rows on the matrix A. So let's let A be n rows by what? How many columns? Well, it could be anything. It doesn't have to be m, it doesn't have to be n, it can be anything, so we want to make it arbitrary, and we're going to choose R. Again, you have to do proofs arbitrary. I can't let B and C be size 3 by 2 and A be size 2 by 7 or something like that. I can't look at specific examples. Right? I have to prove it true for any matrices where, of course, these operations are indeed defined. So the operations would be defined. And when we look over here now, notice since B and C are size m by n, then their sum, what B plus C, is size m by n as well. And when I multiply B plus C times A, B plus C times A, B plus C is m by n, A is n by r. Notice I can do the multiplication, right? The inner number is the same. What's the resulting size? M by r. Okay, so that's, this side is m by r. What about this side? Well, clearly BA, let's say also, I guess. Also, on the other side, right, BA and CA. Look at those products. Since B and C are both m by n, and A is n by r, again, the inner numbers match. We can do the multiplication, and the resulting size of each of these is m by r. Size, I should write, but they're both m by r size. So that the sum of those two, BA plus CA, which is what we're looking at on the right-hand side there, is size m by r, right? So adding these two same size matrices gives us that size. And that's good because this matrix on the left side of the equation is m by r, the one on the right is m by r, so they're the same size. So that's the first thing you have to prove, that they're basically the same size. And you do that, yeah, with sentences, right? You're writing, you're just talking about, just work through it, right? You start with defining the size of each matrix involved so that the operations defined in the property can be done, and then you build, so to speak, right? I'm building as I go. B plus C is this size, and therefore B plus C times A is this size, to get the size of each matrix on either side of the equation. Now, once you do that, now that we know they're the same size, we simply have to show that their corresponding entries are the same. So I'm going to look at this arbitrary ij entry of this matrix and show that it's equal to the ijth entry of the matrix on the right-hand side. So I want to look at the ijth entry of this, And remember, we talked about, here's in general, right? So in this case, notice the B plus C is the A, and the A is the B. So don't get too confused how that's going to work. So to do this, I take what? The ith row of B plus C and dot it with the jth column of A. So the first entry in the ith row of B plus C would be what? BI1 plus CI1, right? Because B plus C, we add corresponding entries, right? And then the first entry in the jth column of A would be A row 1 column J. Remember, it's row column. So row I column 1, or the ith row of B's first entry, and same with the ith row first entry of C, and then the first entry in the jth column of A. So then we're going to add to that the second entry in the ith row of B plus C is BI second column, right? Moving across the row, remember we're going to the second column, CI2, and then the second entry in the jth column of A is a second row jth column. Okay, and I keep going, right? Dot, 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 until I get to the end. Now, what's the last entry in the ith row of B plus C? What's the last entry? Well, we're going across the ith row. How many columns is B plus C? How many columns is B plus C? It's n by n. There's n columns, And so the last entry will be BIN, and the last column is the nth column. Right? And then going down the jth column of A, right, we go down the column, the last entry will be the last, the last row. How many rows are in the matrix A? How many rows in the matrix A? How many rows? N rows, right? R columns, N rows. So the last entry is A, nth row, jth column. And you can see how these numbers are incrementing, right? Where the 1s are, where the 2s are. If we kept going 3s, 4s, all the way down to the last entry. So dot, dot, dot is important because there's several we're leaving out. In general, we don't know how actually big n is, but this is the in general expression. Okay, now the A, B, and C, capital A, B, and C here, these are matrices. Now the B, little b, I1, sub I1, CI1, all these are real numbers. These are the entries. So I can use the properties of real numbers now. Okay, so we just can't assume, right, and just prove, well, we just use the distributive property, we get it. These are matrices. We don't know. We're trying to prove that this property actually works. And it's not clear, as I said, all properties aren't working. We'll talk about some of those that aren't working. Matrix multiplication, right, for instance, we'll show in just a minute, again, is not commutative. So we just can't assume these things. But now we can use the property of real numbers. And what I'm going to do is I'm going to distribute here the A sub 1j, right, over the sum. So I'm going to get BI1A1j plus CI1A1j. Okay, just distribute. Distribute here as well. I'm going to go ahead and distribute all of these. A2j plus CI2A2j plus dot, 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 right? Plus what we get down to the last one is going to be BINANJ plus CINANJ. Okay. So where are we trying to get to? Or don't forget where we're trying to get to. We're trying to get to the ijth entry of BA plus CA. And we're almost there. To see it clearly, I'm simply going to rearrange. If I'm adding a bunch of real numbers together, can I rearrange the order I add them in? Yeah. For instance, 3 plus 4 plus 2 is the same as 4 plus 2 plus 3. Is the same as 3 plus 2 plus 4. It doesn't matter the order we arrange them in. So I'm going to first group, if you will, and add together all the BA combinations here. BI1A1J plus BI2A2J plus dot, dot, dot. The last one is BINANJ. Okay, so I kind of grouped all those together, plus what am I? The other group is just the CA combinations, if you will. CI1A1J plus CI2A2J plus dot, dot, dot again, and the last entry is CINANJ. A, and J. Okay, so I've regrouped in this way. It's the same thing. That's all I've done is distributive property, just regroup. But now look in this parentheses. What do I have? BI1, BI2, BIN. That is the ith row of B. Those are the entries along the ith row of B. And A1J, A2J, all the way to A and J. Those are the entries along the jth column of A. So this is the ith column of B dotted with the jth column of A. Right? So what is that? That's the definition of what? B times A. Not A times B, but B times A, right? It's the ith row of the matrix on the left times the jth column of the matrix on the right. So this is BA. Right, the ijth entry of BA. That's what this whole thing is, right? Everything in here. Everything over here is what? The ith row of C dotted with the jth column of A. That's CA. IJ. And if I add the ijth entry of BA to the ijth entry of CA, then that's nothing more than the ijth entry of BA plus CA. And that's what we were trying to get to, if you remember, right? Going back to the original statement, right? BA plus CA is what we're trying to get to. So this is the arbitrary entry, ijth entry in this matrix is equal to what? All the way the other matrix on the left-hand side of the equation. So that's the end of the proof. Okay? So two things to prove. Prove that they are the same size, and then prove that the arbitrary ijth entry of each matrix is the same. Okay, so that was a little adjustment. I want you to use this. Make sure you rewatch it or whatever and practice the problem you do be very similar to this one. Okay, very similar to this one. Okay, I want to look real quick before we stop this video at some properties that do not apply. So I've already mentioned this one. The commutative law does not apply to matrix multiplication. We looked at examples where you can multiply A times B, but you can't even multiply B times A because that middle number doesn't match up. But here's an example where you can multiply both ways. Here's matrix A, it's 2 by 2. Matrix B is 2 by 2. They're both square matrices of order 2, right? And so I can multiply in either way because, again, the inner numbers will be 2 in either case. AB would be this. Remember how I do multiplication? 2 by 2 times a 2 by 2 is going to give me a 2 by 2, right? And so remember how that works. If you're multiplying, these numbers have to match, right? They're equal, and then these numbers give us the resulting size 2 by 2, right? And the first entry is what? The first row dotted with the first column. So -1 times 1, 2 times -2. That's -1 plus a -4, which adds to -5. This entry 8 comes from what? First row, second column. -1 times 0 is 0, 2 times 4 is 8. Add those up, I get 8. This entry is what? Second row, first column. 0 times 1 is 0, 3 times -2 is -6. And then second row, second column gives me this 12, right? Okay, so that's A times B. Here's the matrix. B times A, I'm going to swap the order, okay? I can still multiply though, right? If I swap the order, I'll still have the same resulting size. But this time, I'll let you check and make sure you understand how I get this result. You get this result. Take a look at the results. A times B versus B times A. Are they the same? No, they are not the same matrix. And so notice, A times B is not equal to B times A. Even though both products are clearly defined, they are not equal. And that's problematic. When you're doing algebra with matrices, you've got to be very careful because with real variables, right, like if X and Y represent real numbers, we're all the time rearranging, right? X times Y, Y times X, same thing. But not for matrices. So if you're doing algebra with matrices, you cannot switch the order. Please, please, please make note of this. Make a little flashcard, do something, and remember this fact. It is never true. It doesn't matter how many matrices you're multiplying in a row. You cannot change the order. You can regroup, but you can't change the order. Okay. A couple other things. The zero matrix. Introduce you to the zero matrix. Very simple. It's a matrix whose entries are all 0. Okay. And in the text, it will denote it as a slanted 0 to make it different from the real number 0, but here are some examples of 0 matrices that can be different sizes. And it has a property like the number 0 for real numbers. So here's some properties. Obviously, if you add any matrix to the 0 matrix, you're going to get the original matrix back. If you add a matrix and then -1 scalar multiple times that matrix, you're obviously going to get the 0 matrix. It's kind of like subtracting A minus A. Here is the real number 0. If you scalar multiply any matrix by the real number 0, obviously you get the 0 matrix. And here's true, if you have a scalar multiple of a matrix and the result is the 0 matrix, then that means either the scalar multiple C is 0, like in this case, or the matrix A is 0, or both. Obviously, it could be another thing. So those are some obvious properties of the 0 matrix. So with that, a couple more rules, and we'll finish up with this particular video. In real arithmetic, right, we have the cancellation law. For instance, if you have AB equals AC and A is not equal to 0, you can divide both sides by A and you get B equals C, right? We do this all the time. Like if I have an equation that says 3x equals 12, 3x equals 12, well, you'll divide both sides by 3 and you'll get x equal what? 12 divided by 3, 4, right? And so we use that property all the time. But it doesn't apply to matrices. It doesn't apply to matrices. So consider this example here. I've got 3 2x2 matrices, A, B, and C. And I look at the product A times B, so I grab matrix A, matrix B, multiply them together, you get this result. And you should verify that. A times C, if I multiply A times C, I get this result. Okay? So take a look at this. Notice that A times B, right, this matrix, and look at that, it's the same as A times C. They are equal. And the matrix A is not the 0 matrix. I'm going to kind of emphasize that that's the 0 matrix. There's that slanted, right, 0. Right? It's not the 0 matrix. 0 matrix has all the entries 0. There's a couple zeros in it, but it has to have all 4 entries would have to be 0. So it's not the 0 matrix. I mean, even if just one entry was not the 0 matrix, still same thing, right? And so A is not 0, but B, the matrix B, and the matrix C are clearly not equal. So notice here, I can't just, assume if AB times AC, or AB and AC are equal, that B equals C. Okay? You can't assume that if A is not equal to 0. Okay? And that's really different. So it's a cancellation laws work for real numbers, but not matrices. And here's one more to close with. It's kind of different from what we're used to. The zero factor law. For real numbers, if I have A times B equals 0, then either A is 0 or B is 0, right? Or both, right? If you have a product of two numbers that equals 0, at least one of them has to be 0. We use this all the time in solving equations by factoring, right? If I have something, I factor it, set each factor equal to 0, and I can solve that equation. It's not always true with matrices, right? Here's a matrix A and a matrix B. Neither one is the 0 matrix. But when I look at A times B, what happens? Let's do this. Let's see if we can do this. It's 2 by 2 times 2 by 2, so I get a 2 by 2. And what's my first entry going to be? First row, first column. Look what happens. 0 times 1, 5 times 0. Both those products are 0. Add them up, I get 0. First row, second column. What's going to happen? 0 times 2, 5. Same thing. Second row, first column. Second row, first column. What's going to happen here? 0, 1, 6, 0. Also 0. And second row, second column. What's going to happen? 0. Right? And so notice that I have an example where AB is equal to the 0 matrix, but A is not equal to the 0 matrix, and B is not equal to the 0 matrix. Oh my goodness, that is really different, right? And so this is a property that doesn't apply. So there are these properties that don't apply to matrices that we're used to seeing with real numbers, and we're going to have to train ourselves to be careful not to make these sort of mistakes when we're dealing with matrices, when we're doing the algebra, right? If you're solving, maybe you got an equation, find Find the matrices that satisfy this. Well, you just can't assume that they're the zero matrix. Neither one of them may not be the zero matrix. And that's really different. Okay, we'll look at some more properties. In particular, we're going to introduce the inverse of a matrix in the next video.